Hello and welcome back to the Science of Concrete Materials class. This is lecture number 21 of the class, and we will continue our discussion on the chemical admixtures. Today we will look at the water-reducing admixtures and maybe the set control and admixtures, depending how long the lecture will run. If not, I will have a fourth lecture on the chemical admixtures topic to cover the remaining admixtures. Okay, so let's look at the water reducing admixtures. Of course, as the name implies, a water reducing admixture lowers the water required to attain a given slump. That is, it reduces the water demand of the concrete. This property can be used to advantage in several ways. First, achieving the desired slump with less water at a constant cement content, means an effective lowering of the water cement ratio, with a consequent, general improvement in strength, impermeability, the water tightness, and durability, reducing the water, that is. Alternatively, the desired slump may be achieved without changing the water-cement ratio by lowering the cement content. This may be done for economic reasons, by cutting back on the most expensive ingredient of the concrete, which is the cement, or for technical reasons, such as lowering the heat of hydration of the concrete. Finally, a water-reducing admixture may be used to increase the slump without increasing cement and water contents, to facilitate basically placements in difficult situations. When used in this way, it is sometimes referred to as a plasticizer. So look at this graph. As you can see here, this curve here, it gives the water content in kilogram per cubic meter, and it gives here the flow table spread, which is basically a measure of the slump. So here, this curve without the addition of any superplasticizer, as we increase the water, the flow increases. So what we can do at fixed water content, without changing the water content, we can increase workability, the slump, basically by adding superplasticizer. Or what we can do, reduce the water content, and just maintain basically the same slump. The same slump we get with less water content. In this case, we get the benefit of additional strength and better durability. So let's look at the composition of these admixtures. The regular water reducers can be divided into three types, based on the general composition of their active ingredients. These are first something called the lignosulfates. The second is the hydroxycarboxylic acids and their salts. And the third one is the hydroxylated polymers, basically derived from hydrolyzed starch, or referred to as polysaccharides. I know it's complicated chemical names, but that's what they are. So most superplasticizers are basically low molecular weight synthetic polymers containing oxyacid groups attached to a carbon backbone at regular intervals. Most commercial admixtures belong to one of the four polymer types listed here. The first one is the sulfonated naphthalene formaldehyde condensates. The second one is the sulfonated melamine formaldehyde condensates. The third one is the modified lignosulfates, which is, purified to remove undesirable side effects. And the fourth one is the carboxylated acrylic ester copolymers, or otherwise polycarboxylates. So the acid groups, are responsible for basically producing a negative surface charge on the cement particles, and thereby dispersing the particles by electrostatic repulsion, as in the case with conventional water reducers. In the case of superplasticizer, being bulky molecules, they provide steric repulsion as well to achieve complete dispersion. And this may be the major mechanism in the case of the polycarboxylates. These compounds have long graft side chains attached to the carbon backbone, giving the molecule a comb-like appearance, for example. So let's look at the mechanism of these admixtures and the mechanism of the water reduction. Water reducing admixtures are basically negatively charged organic molecules that adsorb primarily at the solid water interface. The solid particles basically carry residual charges on their surfaces, which may be positive, negative, or both. And the cement paste, opposing charges on adjacent particles of the cement can exert considerable electrostatic attraction, causing the particles to fluctuate, as you can see in this figure. I'll come to it in a minute. Okay. So a considerable amount of water is tied up in these agglomerates and adsorbed on the solid surface, so leaving less water available to reduce the viscosity of the paste and that of the concrete eventually. So the molecules of the water reducing admixtures interact basically to neutralize these surface charges and cause all surfaces to carry a uniform charges of the same sign. Particles now after this repel each other rather than attract, and remain fully dispersed in the paste, as you can see here in this. This is after the water admixture is added, and this is before. The particles here, the cement particles, basically fluctuate and tie up the water molecules between them. When the cement particles are charged with a like sign, they repel each other, and the water is freed basically to participate in the reduction of the viscosity of the paste. So, as a result, more of the water is available to reduce the viscosity of the paste, and that basically of the concrete. These surface interactions are most noticeable with the fine cement particles and the mineral admixtures, since the tendency for fluctuation is common to all finely divided solids. For example, defluctuating agents or plasticizers are commonly used with clay water systems to produce, free flowing slurries at low water contents. Okay. The use in concrete technology basically is analogous to that use in the case of the clays, and some cases also it involves the same chemicals. So some of the newer admixtures use negatively charged polymers. In this case, the bulky nature of the adsorbed molecules can cause additional steric repulsion, which enhances the repulsion of the between the particles and make the more water available. So basically, let's look at the classification of the water reducers. You know, 3 types of water reducing admixtures are marketed, you know, by several companies, and the capabilities of each are basically summarized right here in this table. You know, there is the improved performance of this, what's referred to as the mid-range and high-range water reducers products, is the ability to add basically sufficient quantities to increase the slump without adversely affecting certain times or air entrainment. Of course, there are impacts, as we will talk about a bit later when we talk about the effects of these admixtures, but generally the case, you know, there is no adverse effects on certain times or air entrainment. Okay, so again, to this table here, it shows the 3 classes of these, you know, low, mid, and high range, which are the superplasticizer. It shows the typical doses and the slump we get, and basically the water reduction here we get with these with each class. Okay, so let's first look at the low range or regular admixtures. These water reducing admixtures, or water reducers in general, are classified as type A in ASTM C494. The retarding type is classified under type D of the same ASTM, and the accelerating classified under type E. And if you remember, we said before, some water reducers also can be retarder or accelerators. One thing to remember, the ASTM C494 is a performance specification that really sets a minimum for the decrease in the water content required to achieve the same slump as a control mix, while basically maintaining other properties within specified limits. So it is performance specifications. Okay, when used to increase workability at a given water content, they are acting as plasticizers. In this case, no limit are set for an increase in the slump at the same water content. Okay. According to ASTM C494, you know, an admixture can be classified as water reducing admixture if it reduces the water requirements by 5% under, you know, this criteria. And, you know, many air entraining admixture in this case could also be classed as water reducing admixtures, considering this criteria, as I said. The regular water reducing admixtures achieve reductions of maybe 5 to 10% in water requirements at normal dosages. The water reduction achieved at any dosage depends on the type of admixture, cement fineness, mix proportions, temperature of concrete, and the time of addition. So see, many variables. So you always have to be careful when using any admixture in general. So, and again, even the composition of the cement, you know, as we said, can be important, not only the fineness, as it has been found that water reduction is lower for cements with high C3A or alkalines. And that is, you know, during the early hydration of C3A, the admixtures can be removed from the cement surface by being absorbed on the hydration products, as we will see later. So again, many variables that impact the dosage, and we have to consider everything. Okay, the second one is the mid-range water reducers. These admixtures, you know, our admixture companies, now offer formulations that function, best in the slump range of 125 mm to 200 mm, 8 to 5 to 8 inches. That is, between conventional concrete and flowing concrete, somewhere in between. As I said, they are referred to as mid-range water-reducing admixtures. Although this classification is not really recognized by ASTM C494, but nonetheless, we're talking about performance specifications. So as an engineer or as a ready-mix supplier may choose to use them for whatever particular situation there is. This third category is the superplasticizers or high-range water-reducing admixtures, HRWR, if you see this abbreviation. So these are admixtures that can achieve much higher amounts of water reductions, about 12 to 30%. And they are referred to as high-range water-reducing agents, according to ASTM C494. We have different versions of it. For example, the type G, which also retardant admixture, okay? These admixtures are used frequently to produce high-strength concrete, since workable mixes with water cement ratios well below 0.4 are possible. So these same admixtures can be used, without reduction in water to produce concrete with very high slumps in the range of 150 to 250 mm. So at these high slumps, concrete flows like a liquid and will fill the forms efficiently, requiring very little vibration. I know, it works like magic, really. Also, highly workable mixtures are called flowing concretes and require slumps to be in excess of 190 millimeters, about 85 inches. This is the reason, for the common name superplasticizer, which is basically universally used outside the formal documents, but will be used here in the context of our discussion. Okay, so the name superplasticizer really, like I said, it's outside the formal documents. Just remember that. Okay, so when used for this purpose as superplasticizer, they must conform to ASTM C 1017, which sets a performance limit in terms of an increase in slump, increase more than 90 mm or 3.5 inches. So there are no fundamental differences between admixtures, conforming to ASTM C1017 and C494 specifications, and most commercial products will meet both requirements. So, and the reason, for two specification is the convenience of specifying specific performance criteria in terms of plasticizing effect. So basically, that's just you need to remember. Here I'm showing, a summary of the classification. Again, if we go back to ASTM C494, the low-range water reducers, which is, water reductions of 5% minimum. And the chemical makeup for these is the lignosulfonate, the type A, the normal, type D, reducer and retardant, type E, reducer and accelerator. We have the high range water reducers, which the water reduction of 12% minimum. Again, the high range water reducers, or superplasticizers. Examples of these are the synthetic polymers, the naphthalene, melamine, or acrylate-based products. We have the type F, which is the normal superplasticizer, and the type G, which is, superplasticizer, high-range water reducer, and retardant at the same time. Okay, so let's look, we know these products, we talk about them, they really, they do a lot. And if you have seen what they do in the field in terms of making the life of the concrete workers and the construction workers. It makes their life much easier in terms of replacing, consolidating and vibrating the concrete. Nonetheless, we need to understand their effects on our concrete, on the fresh and the hardened concrete. So let's look at their effects on the fresh properties of the concrete. Let's look at the flowing concrete and how it affects the concrete by making it a flowing concrete. So concretes with very high slumps, we said, can be used to advantage in difficult placement. As I said, sections, with very congested reinforcing steel like a beam or a column, okay, and also in placement where adequate vibration cannot be achieved. For example, underwater placement, or basically to improve the ease of placement, for basically making pumping easier and more efficient. So slumps exceeding 150 millimeters or 6 inches can be achieved, with conventional water reducers only by using over-sanded mixes with very high cement contents. But the use of superplasticizers allows higher slumps to be achieved using mixed proportions typical of normal slump concretes without the occurrence of excessive segregation and bleeding. Such flowing concretes, though, are particularly well suited, as I mentioned, for tremie placement or rapid pumping concrete and self-leveling in flat work, basically in slabs and similar. So a reasonable starting point is a conventional mix with a slump of 85 millimeters, about 3.5 inches. That is designed for pumping, meaning has a slightly higher sand content. The admixture is added after initial mixing to bring the slump to the desired level. This is in contrast to the use of other admixtures that are added with the mixed water. So this is the flexibility of these admixtures, okay? So if the concrete is really overdosed with a superplasticizer, it may result in a mix that is so fluid it may segregate. So you have to keep that in mind. But fortunately, this problem can be corrected by continuing mixing until the concrete stiffens enough to regain its cohesive properties. Okay, but nonetheless, overdosing is not a good thing. And again, in order to avoid any surprises, as I said, testing and trial batches on the same materials specific to your jobs is key to make sure you do not get surprised. Okay, so that's what these admixtures can do. Basically what they do, they result in a concrete that we call flowing concrete. They make handling of the concrete much easier. So let's look at the slump and the slump loss. What the effect of these admixtures could be. A rapid rate of a slump loss can be a major problem with superplasticized flowing concrete, as we will see on this figure here. So while slump loss is a problem with any high slump concrete, it may be even aggravated by the use of some superplasticizers. And again, to avoid surprises, test the product you intend to use. This problem can be overcome by adding a second dose if necessary, at the job site under controlled circumstances, or by delaying the initial addition of the admixture until just before placement. Make sure to avoid slump loss during the transit mixer travel between the mixing plant and the job site. Repeat additions are possible without compromising concrete properties, as I will show you in the figure on the next slide. Provided that the admixture is properly blended into the concrete in the transit mixer well before it is placed. Incremental additions can be also used, and again, all this has to be controlled, and it's better be done by the ready mix supplier personnel, representative of the job site, or by even the admixture supplier himself to be consulted for such actions. Okay. So again, as I said, I repeat what I said, care must be exercised when adding the admixture at the job site. It cannot just be added by anybody at will. It has to be controlled. Okay, so if you look really at this figure, and you see how the slump loss can be overcome by delayed or second addition. You see these, for example, all these curves, except curve number 4, are concretes with a slump of 225 mm, 9 inches. The dosages, adjusted to give same high level slump for mixes, basically 1, 2, and 3. Okay. So high slump, control mix number 2 requires water cementitious ratio of water cement ratio of 0.6. Okay, this is a control mix with water cement ratio 0.6. This is a control mix with water cement ratio 0.4, 0.45, 2 and 4. Okay, so the rapid slump loss, for the sulfonated naphthalene formaldehyde condensate, which is SNF abbreviated, admixture. This is number 3 here. See the slump loss here of curve number 3 can be compensated for by a second addition. Look at it. Here we have a second addition. We ended up, with curve number 5, as you can here if you track it. Curve number 5, you see, we reduced the effect, of the slump loss in this case. Or maybe the delayed addition to low slump concrete. Look at curve number 4 here, and we, instead of a second addition, we delayed the addition. As I mentioned earlier, we could delay the addition rather than having a second dose. And you can see also how basically that also reduced the slump loss. So there are more things that you can do about, the delay addition or the second addition or incremental additions, just to make sure we maintain the slump sufficient for placement and handling. Also, you need to remember, sometimes admixtures that, also have retardant tendencies can cause workability problems, basically due to acceleration of the early hydration of C3A. So in extreme cases, flash set can occur. So delaying the addition of the admixture will often, alleviate this problem, or maybe an alternate admixture can be used. What I have to say, retempering concrete with water to restore workability is an absolutely rejected practice, because it will result in the increase of the water cement ratio. As I said, using additional water reducing agents and an additional dose of admixture, during retempering can reduce or eliminate the need, for further water. Do not add water. Just make sure the dosage of the admixtures are planned to be added at certain times to maintain the slump for easy placement. Okay, that's what I have to say about this. Do not just do it at will. The retempering with water should never be done, and the incremental addition or the delayed addition of the admixture should be planned and should be decided by the ready mix supplier or the material manufacturer. Okay, so let's see what the effect on bleeding and air entrainment. So when, while water reducing admixtures, improve the workability of concrete, as measured by slump, they may not necessarily improve cohesiveness. And like you said, maybe in the introduction lecture about the difference between cohesiveness and slump. Admixtures based on the hydrocarboxylic acids tend to increase bleeding and should be used with care in high slump concretes. That's one thing you need to remember. So although well-designed flowing concrete made with superplasticizers will not segregate, overdosing must be avoided since it will cause excessive bleeding and segregation. And I've seen that, trust me. I have seen these problems in the field, and everybody scrambled to explain why, when, how, where, and all of that. I thought, based on my reports, the lack of appropriate testing and trial batches before the use of admixtures, or could be due to the addition of admixtures at will without control. So okay. So the lignosulfate-based admixtures, as I said, tend to bleed less because they entrain air. And that's one other thing here. We're talking about side effects. So any regular water-reducing admixture, regardless of its own air entraining ability, will reduce the amount of air entraining admixture required to attain a given air content if it is added at the same time only. So again, many trial batches and testing should be done to verify all that. This is because the air entraining admixture is no longer adsorbed on the solid surfaces of the cement, and it is thereby wholly available to act at the air-water interface. You see the interaction we talked about the interaction of the admixtures. Okay, so on the other hand, superplasticizers have air detraining properties, and an air entraining agent must be added to the concrete to get stable air void system before a superplasticizer is added. Okay, so again, testing, verification of the interaction between the admixtures, and understanding basically the literature, the documents that come from the manufacturer as to the interaction between the various admixtures. Okay, so as with regard to the retarding of set, many of the regular and some mid-range water reducing admixtures will also act as retardant admixtures. So if prolonged setting times are not convenient for whatever your situation is, the admixture can be formulated with an accelerating admixture to counteract the retardant tendencies, or even to provide some net accelerating effect on the setting if needed. However, though, non-retarding formulations sometimes show also a tendency to cause retardation at low curing temperature. So it has been found that delaying the addition of the admixture until a few minutes, after water has been first added, will increase the potential water reduction, and enhance air entrainment, and also increase the retardation of the set. If this, occurs in regular additions. Okay, so again, manipulating the times of addition, planning them correctly, testing your admixtures and the interactions with other admixtures allows you to make any adjustments to the concrete mix, to the dosage, to the time of addition, all before actually you are ready to pour whatever concrete members you are trying to pour. All this has to be done before. So let's see what are the effects on the concrete and the hardened concrete properties. And of course, most and foremost is the compressive strength. Okay, when admixtures are used to lower water requirements, increases in compressive strength can be anticipated, which is a good thing. These increases, can be observed in as early as 1 day, if excessive retardation does not occur, of course. So it is generally agreed that increases in compressive strength up to 25% greater than would be anticipated from the decrease in water cement ratio alone. Why? Probably, this reflects basically the development of a more uniform microstructure when the cement is dispersed uniformly. So some refer to this phenomenon as increasing the efficiency of the cement. So this is another advantage of these admixtures. So when used at low water cement ratios, superplasticizers can modify type 1 cement to behave as super high early strength cement, exceeding even the strength gain of a type 3 cement. So imagine, when we remember what we said before, sometimes there are other substitutes to using different type of cements. By using these additives and the admixtures, they can do wonder for us, trust me. So it should be emphasized that this is the result of both a greater cement efficiency and a greatly reduced void content. The rate of hydration need not be increased, but we, as I said, we are reducing the void content. So unlike type 3 cement, the more rapid strength gain as a result of reducing the water cement ratio by using these admixtures will not be accompanied by an increase in the rate of heat evolution. So if lower cement content used, of course, then we gained another advantage by lowering the heat of hydration. So again, the refinement of the structure, the better packing and densification of the concrete matrix will go a long way in improving strength and durability, which is as a result of using these admixtures, again, used correctly and efficiently. So basically, when we talk about high strength, concrete, very high strength can be achieved when water cement ratios are lower, below 0.4. Again, the advantage of using superplasticizers or water reducers. To do this economically and without excessive generation of heat, requires the cement content to be kept to normal levels while providing an acceptable slump. So basically, we do not add cement, we maintain the same cement content. Basically what we do, we reduce the water content. Eventually we reduce the water cement ratio. Okay, so superplasticizers are well suited to achieve these objectives, and they are used in most concretes with 28 day compressive strength exceeding 80 MPa or 11,000 psi. This only could be done with superplasticizers though. So the low water cement ratio also, again, improve the rate of strength gain at early ages and can be very useful in the precast concrete industry. So after 24 hours of normal curing, it is possible to obtain compressive strength that take 8 days to develop using a higher water cement ratio, such as 0.5, for example. Even, larger gains are realized, of course, if a steam cure is used. So again, the point to take away from this, when we reduce the water cement ratio or the water content, we automatically increase the strength, refined the microstructure by reducing the voids, by decreasing the void content of the concrete or the paste matrix, and that by itself, considered a great enhancement to the concrete durability and performance. And of course, if we also at the same time lowered the cement content, not just the water content, okay, we may not achieve the same strength level, but we did at least reduce, for example, the heat of hydration or the rate of heat generation. And also at the same time, when we reduce the cement, you reduce the paste content. And that's automatically will result in other advantages, such as the reduction in shrinkage eventually. Remember that. Okay, so let's see what the effect on other hardened properties of the concrete, So it is often stated that water reducing admixtures increase the drying shrinkage and creep of concrete. However, the data are conflicting, as reported in the literature, and depend very much on the cement type and the particular admixture. And again, this really has to be related to the amount of the cement. As I said, reducing the amount of the cement and the water results in reduction. But generally, there is no rule of thumb, and there is no clear indication on the literature as to the effect. So an increase in the rate of shrinkage is often observed after 90 days of drying. There is little difference in shrinkage compared to control concrete. Okay, so that's, like I said, really not clear data in the literature. With creep, the situation is less clear, and different admixtures may increase or decrease creep. So if drying shrinkage or creep values are critical, then tests should be carried out to assess the effects and the design design the concrete basically to reduce the values if necessary. So again, this is a more complex issue, but you need to know about it. But as we said, the reduction of the water cement ratio and the creation of a more uniform pore structure means that the permeability, as I just mentioned earlier, permeability of the concrete can be reduced by the use of water reducing admixtures, with a general improvement in durability, just automatic. So concretes must, of course, be air entrained for frost protection, as we said, if concrete is to be exposed to freezing temperatures. But in that case, the spacing factor required for good frost resistance is found to be higher than the value required for conventional concretes without water reducing admixtures. I am not going to, this, as I said, this statement may not be universally accurate, but again, I would hold judgment on this one based on a case-by-case basis of trial mixes and the interaction of admixtures done, with trial mixes and tests. Okay. So what I would do now, though, I will stop right here, and I'm gonna have another lecture to cover the set control and admixtures, the retarders and accelerators, because again, the lecture get too long, and I want to avoid very long lectures. So I will stop right here. So this will be the end of lecture 21, and we will have another lecture number 22, to finish the topic of the chemical admixtures. Thank you for watching, and I will see you next time.